situation, and you don't expect it to be more than 2D and more than 2 elements. And it turned out that when you do 2 elements, it doesn't train so well. But then when you change it to like other versions of constraints, some of them don't train so well, or it takes a long time to train to approach similar behavior. So I believe that we haven't actually tested if you force it and just like regardless of whether it's training well or it doesn't produce such a good predictions and still go for the equations, what happened with the equation had changed. I suspect it would, because the predictions won't be as good as, you know, the L1 constraint, because the predictions isn't as good. So I don't expect it to be as accurate a formula. So that's my expectation, but we didn't actually do the experiment and say, okay, just forget how bad it is training or how bad the prediction is, and just went ahead and do the symbolic regression part. Hope that helps. And
sure.
Thank you
Thanks.
for staying, and you know, those who are really sleepy, this is amazing. Thank you so much for doing all this.
Thanks, Shirley. Let's go to this. Second question is also to Shirley on how are the results validated for the case of the Halo density estimation? I think it's the last example that you showed us. Is it on another simulation, particle resolution, so on?
Okay. So for the particular formula, we just validated it with like a different simulation, but it's the same resolution. So we didn't change the simulation resolution. We didn't change the simulation, say, cosmological constant. So like one of these latent variables that will affect the simulations, for example. So we didn't change all of that, which we could, but we were very intrigued, to say the least, by the formula as a scientist, because we cannot explain it ourselves. So we feel like we should really try to understand the formula, I mean, the analytical expression we achieved, and go further from there. So right now we have analytical or phenomenological expression that works for certain simulation sets, but we have not got to understanding. So we got really intrigued by, can we get some kind of understanding there? So that's where we are right now.
Yeah. I think the question here would be, it would be interesting if the formula was invariant to the resolution. So, I mean, as you change the resolution, you know, you basically bring in different parts of this power spectrum into your final simulation. So if you start to include much smaller halos and so on, is your formula going to remain the same given everything else? So I think that would be kind of
really excellent to try. We just haven't tried it.
All right, great, thanks. There are other questions for Shirley, but I think we will move on to a few other speakers, and if you have time, we'll come back to Shirley. It's a question to Nigel. Is could you explain briefly how phase diversity works? Is Nigel around? Sorry, I should have checked. Unfortunately, I see that he is not present here right now, so we'll have to hold on. Then here's a question for Tony. What about an iterative procedure for parameter fitting? Start with a few Gaussians, get the principal curve, sample the curve for more Gaussians, get the new curve. So if Tony is around.
Yes, sorry, do you hear me?
Yeah, I hear you.
Could you repeat the beginning of the question? Sorry, it dropped.
The question is, what about an iterative procedure for parameter fitting? Start with a few Gaussians, get the principal curve, sample the curve for more Gaussians, and get the new one. I think what they're getting at here is that you showed us how you fit this mixture of Gaussians. And the question is whether you can start with fewer Gaussians in the beginning and then use those Gaussians to sort of infer your principal curves, and then use those principal curves to add in more Gaussians and do this in an iterative way until convergence. Because I think one of the issues is about, you know, how do you exactly choose your K? I think it was your parameter K is the number of Gaussians that you would like to use to sort of fit the simulation. Have I made the question clearer?
Yeah, exactly. Sorry. So yeah, indeed, K is chosen a priori right now. So basically, we choose it using an initialization that is based on the minimum spanning tree computed on the halo or galaxy themselves. And we just cut some branches, short branches of it, and it's usually close to the number of halos that is inputted in the graph in the algorithm. And this is indeed what makes the computation quite heavy sometimes, because it scales with n squared times k. So if you have a large k, this is computationally heavy. So this could be a nice idea to start with a few k's, a k that is small, and then trying to increase it. Yes, indeed. Okay. But yeah, it could work. Yes. Okay. That's a great idea, I guess.
Nice. We'll continue with you. I think you might have answered this question. Is, can we use the minimum spanning tree as the initialization of the Gaussian clusters? And if you do,
exactly, this is
that's what you do. All right.
Yes, that's what I'm doing. I didn't say it in the indeed in the talk, but that's what I'm doing.
Okay, so that answers the question. Great. And then, have you compared your method to other sort of manifold discovery schemes like Laplacian eigenmaps or something else?
No, this is not something we have been doing. We have been trying to compare with other structure finders, more cosmological related, that are existing on the market, like Disperse, if some of you know, but no proper method proper to data science or stuff like that. But indeed, it has even in the formalism, it has some similarities with Laplacian eigenmaps and stuff like that. So it could be also something to investigate indeed. Yeah. But not for now, not done.
All right, thank you. And the last question to Tony in this slide is, can you apply your technique to the simulations at different instances of time? And have you done that to sort of study the evolution of some properties of the filaments, like the number of filaments? Can you create some kind of a filament mass function? That's the question.
That's a very good question, because this is something that I'm currently investigating using Illustris simulation and trying at different z to compute the graph and see how its characteristics, its typical length, and the mass of the width of filaments are evolving through time. So this is something I'm currently doing. Yes, and I don't have anything to show concretely, but this is something we are doing. So yeah,
awesome.
That's a good idea.
And we'll wait for your subsequent papers. All right. We'll go back to a question to Shirley. There's a question from Meng. Is imposing the graphical structure basically a way to impose the form of the governing equations of the system?
I would say, any inductive bias, it is a way to inform, the network what the prior assumption we have about the system, right? So in this case, we know that these things are interacting in sort of particle-based or object-oriented base, right? So in the examples I think I gave was planetary system interacting with each other, or balls bouncing in the wall, or a spring which are modeled by multiple nodes connecting with each other and interacting with the mass. So all of these were sort of assuming there is a object-oriented relationship. Instead of like grid-like, it is really particle or like object-like. So I think that is the assumption. And the other assumption that we make, and it's making it obvious to the network, is that you can permute those two particles and it's still there. So permutational invariant at some level. So the forms of the equation at some level is informed by the fact that it is object-oriented, I think, and it is, you can permute those two particles and it's still probably going to do the same for some of the laws. So especially for the gravitational interactions ones. It's not true for all of them. But I think it informs the, what are the players in the equations, right? So that I think is informing it for sure. And for symbolic regression, you can only put so many variables in it. So in that sense, you are informing it by only allowing certain number of variables into the selection procedure for the symbolic regression. It's a great question.
Thank you. I see that there is a question for Grigor as well. Are all the neural networks use MLPs, or do you have any specific architecture? I think in your talk you didn't mention much about the actual architectures that you use. That's why probably this question.
Yeah, hi. Do you hear me?
Yes.
Yeah, fine. So we tried different architecture, but there's no real gain apparently to complexify it too much. And the simple MLP with about, I don't know, 2 or 3 layers works really well. So since the goal is to gain as much computation as we can, we try to keep it simple, and it works well enough that we don't need more.
I see. All right. So I think if there are any other questions here from the audience, just feel free to unmute yourself and ask the questions right now.
I have one.
Yep, Mark has one. Here you go.
Thanks for all the talks. I have a question for Shirley. So one of the big unsolved problems in physics is still seemingly quite simple. It's just hydrodynamic turbulence. And so is there a way to regress the symbolic forms of what would be the right closure equations for turbulence?
This is exactly what we're working on. So we just started working on it. We took very simple simulations, and we basically, the idea is to be able to predict the simulations and make it generalized when you make the box wider. Because when you make it wider, it's actually harder to run those simulations because it changed the cooling time. And then you hopefully will regress to some equations, and maybe that will tell us something about the closures. But we don't know. We're just at the beginning of all that. But I'll be happy to talk to you afterwards if you're interested.
Yeah.
So this is work with Google DeepMind also, actually.
Thank you.
Thanks, Mark. I'll give a few minutes or a few seconds. Anybody else who wants to ask a question? Even if it's the other speakers? Yeah,
If
yes,
no one wants to ask questions, but this is a live Q&A and coffee and tea break, so we can just pause for now and relax. And so the Q&A sessions were advertised to be only for the specific Q&A times, but actually we're just on this live session watching the live stream all at the same time. So feel free to stay on to watch the next blocks of this workshop on this stream. I think you probably agree that it's a little bit more interactive and social here than on the COSPA platform. So yeah, feel free, and we'll see you around. Thanks again for all the speakers and Rajat. Do you have anything else you would like to add, Rajat?
No, I think that's it.
Cool. All right. See you around. I'm gonna mute myself now, and then I'll start the stream at 10 o'clock. If you want to stay here.
Sure.
Okay.
Thanks, everybody.
Thank you. This is really nice. Thank you so much.